Hi, my name is Kirill Bykov, and in this video I would like to introduce you to our work, DORA, Exploring Outlier Representations in Deep Neural Network, that was just accepted to TLDR journal. So deep neural networks achieve state-of-the-art results in various domains, in various problems. However, they often can learn spurious concepts and spurious correlations from the data. These are the patterns that are aligned with the target class in a training data, but are not essentially related to the learning problem. Models that rely on such features, they struggle to generalize, which further leading to the lower performance on data subsets where such correlations do not exist. Often, spurious correlation manifests in artifacts, and these artifacts are often unnatural to the problem. For example, such as the textual watermarks in a context of image classification, or for example, human marks on images in context of medical image classification. So here on this figure, it is an illustration of one specific spurious correlation that was found in a Pascal VOC 2007 dataset, and it manifests as that class horse in the dataset correlated with a watermark. Therefore, once the model was trained on this data, the model learns that the presence of the watermark is connected inherently to the class horse, and therefore, if, for example, the watermark is absent on the image, then it is not classified as a horse, even if there is a horse in image, and vice versa, if you add a watermark to the image of another class, it would be misclassified as a horse. In our work, we talk about the neural representations, and we defined a neural representation as a real valued function mapping from the data domain to the set of real numbers. And neural representations could be thought of as subfunctions of a given model that represents the computational graph from the model's input to the output or activation of the specific neuron. And in our work, we tackle the problem of detecting the malicious representation. So given a model, our goal is to identify the neural representations that have learned spurious concepts. And in order to do so, we hypothesized that since spurious concepts are often unnatural and artifactual to the given task, we can try to first establish a distance measure between representations functions that are inside of the network that measure the similarity between the concept learned by these representations. And therefore, again, since the spurious concepts are unnatural to the given problem, representations that detect spurious and anomalous concept would be outliers in this distance. So this figure illustrates our approach. So the left part, illustrates that after the model was trained, in the intermediate representation, some concepts are learned. The center figure illustrates that introducing the distance measure between neural representations, so function, we try to estimate the similarity between the concepts that were learned within these representations. And the third, the most right figure illustrates that we take this distance that we compute and we analyze, trying to group together neurons that detect similar concepts, and as well trying to find outlier representations that potentially we hypothesize can encode and can learn spurious and undesired concepts. So in our work, center to our work is we propose a new distance metric between neural representation that we named as extreme activation distance. And the main idea of this distance measure is that we try to figure out the similarity between between concepts of two representations by analyzing how these representations activate on each other activation maximization signals. So these activation maximization signals are data points from the data domain that significantly activate neural representations. And intuitively, if two representations are detecting the same concept, then probably they would be very much activating on each other's activation maximization signals. Whereas when two representations are detecting different concepts, their respectful activation maximization signals would not activate the other representation. So this is the illustration of the proposed extreme activation distance. Given two functions, given two neural representation, one is the logic from the ResNet 18 trained on ImageNet, and this is the logic for the class Zebra, so it's pre-softmax layer of the network. And we wanted to analyze the distance with another logic from the same layer, the lionfish representation from the same layer, from the same network. So in order to estimate extreme activation distance, first activation maximization signals should be collected, and they are illustrated on the right part of the figure, with blue for the class for the representation zebra and orange for the representation lionfish. And then we are evaluating, inferencing these images to collect the activation across two representations. And the final distance measure is calculated as a cosine of the angle between what we call as a representation activation vectors. These representation activation vectors are generally vectors that incorporate the information about how two representation reflect on each other activation maximization signals. So here, this representation activation vector is illustrated as a blue and orange vectors in the left scatter plot. So the extreme activation distance, as I mentioned, works as it estimates the cosine of the angle between these two vectors. And the idea is that if two vectors are collinear, that means that both representations are very much activated by each other activation maximization images, then it means that the concepts that we learn by the representations are quite similar. So in this figure, we again analyze the logits, logit representations of the ImageNet pre-trained ResNet 18, and therefore we know the labels of these representation. We know what concept was learned by these representations. So we can see that in the case of a husky and malamute, two very similar looking dog breeds, we can see that their representation activation vectors are very much aligned. However, the further right we go, the less visual similarities there is between classes, and we see that the angle grows. And for the final class, like an aircraft carrier and a Siberian Husky, they bear no visual similarity. Therefore, we can see that their representation activation vectors are almost orthogonal, showing that the concepts behind these representations are very different. And our paper is called DORA, as a data agnostic representation analysis. So as we showed before, extreme activation distance is computed using the activation maximization signals. And previously, up to this point, we only showed that these activation maximization signals could be found from the real natural data, as we call it. However, the progress in the field of activation maximization allows us not to find these signals across the data set, but actually start an optimization procedure to generate the signals using the only model itself. And here you can see on this figure, on this image, you can see that on the left we have most activating images for the neuron 652 in CLIP ResNet 50 network, mostly containing frogs. And on the right, you can see one synthetically generated signal, activation maximization signal that maximizes activation of this particular neuron. Therefore, this, as we call it, synthetic activation maximization distance that based the similarity on the synthetic activation maximization signals allows us to alleviate the dependency on the data and therefore compute similarity between representations without any data set. So as an intermediate summary, in our paper, we propose extreme activation distance that could be computed either by analyzing the natural signals, so in a data-aware scenario, or by analyzing the synthetic signals that do not require the data set. We evaluated extreme activation distance, and we were able to report that the extreme activation distance, specifically the natural extreme activation distance, was generally showed high alignment with the human defined distances, practically meaning that the distances that extreme activation distance yields are similar to how humans perceive distances between concepts in a case where the concepts behind the representations are known. And as well, we demonstrate that the extreme activation distance is very efficient to be used to detect outlier representations in the scenarios where we were able to inject this outlier representations, those representations that detect really abnormal concepts within one specific layer. So extreme activation distance was very useful for this problem. And finally, we demonstrate in a practical applications that the outlier representations that are yielded by analyzing the extreme activation distance often learn to detect undesired concepts. So, for example, within popular ImageNet trained networks, we were able to identify specific neurons that detecting, for example, the Chinese watermarks as well as Latin watermarks. So this behavior we were able to report across three networks: the ResNet, DenseNet, and MobileNet. As well as we also demonstrate that the neurons that are nearby in this extreme activation distance, they also have the capacity of detecting spurious concepts. So in conclusion, in our work, we introduce the extreme activation distance metric that measures the similarity between representations by analyzing how they perceive each other activation maximization signals. We evaluate the newly proposed distance measure in various experiments and demonstrate its practical utility. And in our paper, we introduce the framework of representation analysis. This framework allows to analyze representations in one specific layer of the network and investigate how what relationships there are between neurons, what type of clusters there are. So we propose so-called representation atlases to visualize as a representational space, as well as we propose to perform an outlier detection using the proposed extreme activation distance in order to find neurons that may potentially detect some undesired concepts. DORA, so the data agnostic representation analysis, is a special case of this framework, which allows not to rely on the availability of the data, which is useful in the specific contexts. And in practice, we demonstrate that often these neurons that were reported as outliers by extreme activation distance indeed detect undesired and artifactual concepts. Thank you very much. If you're interested in more detail, you can check out our paper. Again, thank you for watching, and see you.